Lately we've been studying this type of problem, a second order linear differential equation with constant coefficients and non-homogeneous. The right hand side is a function of x. And for good measure, to keep it second order, I'll stipulate that the first coefficient can't be 0, because if a2 was 0 we would have a first order differential equation, wouldn't we? Okay, well, previously we solved this kind of problem by using the method of undetermined coefficients, but that only worked when the function q of x was a polynomial or a power of e or a sine or cosine function or a hyperbolic sine or hyperbolic cosine function. We're rather limited in what the right hand side can be in the method of undetermined coefficients. And for the very simple reason is that we need, for that method, for there to only be a finite number of linearly independent derivatives. So what that means is when you, the method of undetermined coefficients, you start taking the derivative of this function and you'll get multiples, constant multiples of a finite number of derivatives. For example, if you have an e to the 2x, then when you start taking derivatives of e to the 2x, you get multiples of e to the 2x. If you have, say, a sine of 3x, start taking derivatives, you'll get sines of 3x and cosines of 3x's. Only two different type of functions there. In other words, there has to be a finite number of different derivative functions. Because in order to determine the unknown coefficients, the undetermined coefficients, we can only determine a finite number of them. Alright, so I hope that made some sense. But now we're going to broaden the problem to consider what happens when the right hand side is not one of those kinds of functions. Say, for example, it's the tangent function. Q of x equals to tangent x. Well, the derivative would be secant squared x. The second derivative would be 2 times secant x times secant x tangent x. So that's 2 secant squared x tangent x. And the third derivative is going to be yet a more complicated function. And so every time we take a derivative, we introduce functions we haven't seen before. And this would go on forever. It would never end. There would be an infinite number of different derivative functions, which means there would be an infinite number of undetermined coefficients. That would be pretty tough to deal with, wouldn't it? So, with all that preamble, now I'm going to show you the method of variation of parameters, which deals with this situation. And I mentioned in the last video that I think it's worthwhile to watch the derivation of this. I'm basically proving a theorem. And I think it's very good for you to try to see it and watch it. It's a very clever method. It's great mathematics and gives you an idea where all this comes from. Alright, so how do we do this? And I'll probably have to refer to my book because it's kind of long, a little bit long and tedious, and I may not be able to do all this off the top of my head very well, but we'll go for it. Now then, first of all, we need the complementary solution. And you would get the complementary solution just like you would with the previous problems we worked. Set up a characteristic equation, solve for the roots. And for a second order, we would get two functions here. And let's call it C1 y1 of x plus C2 y2 of x. That's our complementary solution. Now this could be e to a power, it could be something, could have sines and cosines, things like that. But anyway, that's what I'm going to think of as a complementary solution. Now I'm going to write out the particular solution this way. Y particular is going to be u1 of x, y1 of x, plus u2 of x times y2 of x. And so I'll introduce two more functions here, u1 and u2. The y's come from the complementary solution. So we're varying these parameters by introducing these new functions. Perhaps that's where the name came from. And my goal here now is to solve for u1 and u2. Okay, and now I'm going to do a little bit of erasing, and just to shorten all the writing here, I'm going to write you know, the u1s and the y1s. I'm going to write these functions without the parentheses x, just so it'll be cleaner to follow. So I'll do that, and we'll get moving on this. So here we are. I wrote that y complementary is c1 y1 plus c2 y2. Y particular is u1 y1 plus u2 y2. And now our goal is to figure out what is u1 and u2. And if we do that, we manage to do that, then we have solved the entire problem, because we have both the complementary solution and the particular solution. Well, our first chore is to take the derivative of y particular, and I've got product rules here. So it's going to be u1 prime y1 plus u1 y1 prime plus u2 prime y2 plus u2 y2 prime. And that's just the first derivative. Our second derivative we also need, and this will be more product rules here. u1 derivative of the derivative is the second derivative, u1 double prime y1 plus u1 prime y1 prime plus here u1 prime y1 prime plus u1 y1 double prime. And that's just the first half. The second half will be u2 double prime y2 plus u2 prime y2 prime plus u2 prime y2 prime plus u2 y2 double prime. So you'll notice that we have some like terms here that we can combine together. So I'm going to do that. I'm going to combine these two terms together, and try to shrink this down. I combine like terms, so y particular double prime is going to be u1 double prime y1 plus 2 u1 prime y1 prime plus u1 y1 double prime. Let me make sure that looks like a double prime. And then we have the same stuff over here with subscripts of 2 instead of 1. So there's the second derivative. Alright, now what do we do with all that? I'm going to, of course, plug all this into the differential equation. And it's going to be a bit messy here. So I have a2 y double prime. I tell you what, rather than torture you with this, I'm just going to write all this out, and then I'll get back to you. Well, I'm back, and I took this differential equation, substituting y particular, so a2y particular double prime plus a1 y particular prime plus a0 y particular, equal to, and I just took these coefficients and multiplied all these terms. And so if you look carefully, this will be a2 times y double prime particular, this whole mess. Here's a1 times the first derivative of y particular, and then y particular is here times a0. Okay, now here's the secret, and you really got to admire that whoever thought this up. I don't know who came up with this method, but it's pretty amazing. The secret is to separate these terms in a very productive way. So I'm going to, I think, erase everything on down. We'll have to remember this stuff here for later usage. But I'm going to take the bottom half and rewrite it up here, reorganized in a different way. Well, here we go. I took this whole mess down here, and I split it up here. And I have to confess, I had to cheat and look at the book, because you know, I wouldn't know exactly how to organize that just off the top of my head. So let's make sure it's right. I have a2 times all this stuff. And out of it, I took, let me chalk these off, u1, y1 double prime, and u2, y2 double prime. That's these two terms. And then we took out a2 times u1, y1 prime. That's one of these. And then I kept another one here. So these two came from that term. And this one came from that term. And then we also have a2 multiplies these two. So a2 multiplies u1 double prime y1 and u2 double prime y2. So that accounts for everything multiplied by a2. And then for a1, we split it up a little bit here. Let me see. u1 y1 prime and u2 y2 prime. And then over here it's a1, we've taken the other two terms, u1 prime y1 and u2 prime y2. And then finally we have this remained intact. Now, this actually allows us to condense this in a productive way. So I'm going to erase this and rewrite that equation a little differently, and I'll explain what I did. Now I've changed this a little bit, and here's what I was able to do. I was able to, and the only thing I really changed was this portion right here. Because if you look real carefully, this whole expression is the derivative of u1 prime y1 plus u2 prime y2. So I have the little derivative mark on the outside of this parentheses. If you take the derivative of these two terms, it'll expand out to these four terms. Alright, so that condenses this whole equation down a little bit, and now I'm going to erase this and condense it down further. Well, I copied this out of the book, this top part, and let's make sure everything's in order here. So what the author has done is to factor out u1 from certain terms involving these coefficients. So let's see where that comes from. I have an a2 u1 y1 double prime. So this term came from here. And then this term, the a2 u2 y2 double prime, appears over here. So these two terms are accounted for right there. Alrighty. Now then, for a1, we have a1 u1 y1 prime. a1 u1 y1 prime is right here. And then of course a1 u2 y2 a1 u2 y2 prime is right there. So we accounted for that. And then we have a0 u1 y1 comes from here. And a0 u2 y2 comes from there. So that wipes out the whole top line, came from those terms. Now what else do we have? Is it just straight copying? I think it might be. a2 times this parentheses is right here. So this parentheses comes from there. And this derivative of this parentheses is recopied up there, so that's accounted for. And then we have a1 times these terms. All right, so it's correct, and we're about to arrive at one of the big punchlines in this whole theorem, which I like. But first of all, do you remember what we're doing? We're trying to solve for u1 and y1 and u2. u1 and u2 we're trying to solve for. And so let me erase this. And I want to remind you that the original problem was this problem. It was a2 y double prime plus a1 y prime plus a0 y equal to q of x. Now, when we solved the complementary solution, we got some constant c1 times y1 plus some constant c2 times y2. Now the complementary solution, you recall, that solves the homogeneous equation where the right side is 0. So in other words, if I plug in y1 into this equation with all its derivatives, the right hand side is going to be 0. Same with y2, because the complementary solution solves everything equal to 0. So that's one of the big punchlines, because look what we have here. A2 y1 double prime plus a1 y1 prime plus a0 y1. Well, that's what you get if you plug y1 into this equation. This equals to 0. And we have the same thing over here. Here's y2. All this is equal to 0. So that changes things quite a bit here for the better. And so now we're down to just this part right here. So after being able to erase the whole top line here, which is all equal to 0 from the complementary solution, we're going to make one more assumption. And this is the other punchline. Notice that these two parentheses contain the same terms. u1 prime y1 plus u2 prime y2. And the only difference is that we have a derivative here and we have an a1 there. Now wouldn't it be nice if those were equal to 0? So we're going to let u1 prime y1 plus u2 prime y2 equal to 0. You're thinking, wow, isn't that cheating? Well, let's see what happens. Can we get something we can work with? So we essentially have wiped out those two. And now we have u1 prime y1 plus u2 prime y2 equals to q of x divided by a2. All right, so here we are. Now, I got to look in the book because I forgot what goes on from here, so hang on. Well, silly me, I already have it. If you look carefully, if we make this assumption, this is one equation, and when we make this assumption, it leads to a second equation. Here are two equations in which the unknowns are u1 prime and u2 prime. And so what I have a system of linear equations. So let me erase this, and we'll use Kramer's rule to write out the answers. Well, I see I had a serious typo here. Maybe you caught it. When I wrote this out, I forgot to put the derivative marks. And so, unfortunately, I've erased everything else it came from. But I think if you went back to the video, you would find that we had a2 times this parentheses equal to q of x. So I forgot to write those derivative marks. Please correct that in your notes. All right, so I took this and put it up here, make it a little more neatly. And if you look carefully, the variables I'm solving for up here are the derivatives of u1 and u2. So u1 prime appears both places here. And because we already know what y1 and y2 are, and we can get their derivatives, because remember, those came from the complementary solution. So y1 and y2 are known from the complementary solution. We can take their derivatives, and we know what q of x and a2 are. We have basically a system of two equations with two unknowns. The unknowns are u1 prime and u2 prime. And the coefficients are the y1s and their respective derivatives. So, I'm going to erase all this, and now we can use Kramer's method, Kramer's rule, to write out a solution. So, if I solve for u1 prime, I'm going to replace the determinant that would be formed from these coefficients, and replace the first column with 0 and q of x over a2. And then I'll use these coefficients, y2, y2 prime. And make that a little more legible. And then the bottom derivative, we'll use these coefficients, y1, y2, and y1 prime, y2 prime. And that's the derivative of u1. And then once we can work this out, hopefully we'll be able to integrate and get u1. And then u2 prime will be the top determinant. Now I'm going to replace the u2 prime column on the right, this column, with 0 and q of x over 2, over a2 rather. First column will be y1 and y1 prime, and the denominator is going to be exactly the same here. It's going to be y1, y2 over y1 prime, y2 prime. So there we go. So here's the good news. Okay, you've sat through and watched all this mess unfold, all this this method of variation of parameters, and the good news is that we don't have to recreate the wheel. We can start with a problem, find this complementary solution involving y1 and y2, take their derivatives, and then we can just plug it into this and solve for y particular. So let's go do a problem.